Good morning, ladies and gentlemen. We are going to start with a video today on harmonic motion. So get some popcorn, make yourself comfortable. Make sure you've got your...
Hey Mark, get set. Here we are at Caltech.
I have a story to tell you. I'm not sure that it's true, but it's a good story, so I'm going to tell it to you anyway. It's about our old friend Galileo. One day, when Galileo was a young man in Pisa, he attended Mass at the Duomo. That's the magnificent cathedral in Pisa, whose bell tower is the famous Leaning Tower of Pisa. In the Duomo, there's a lamp that hangs down from the ceiling by a long cable. And on this particular day, the lamp was swinging back and forth. Probably had just been lighted. And Galileo, being Galileo, noticed something about the swinging lamp that no one had ever noticed before. He noticed that each complete swing of the lamp took exactly the same amount of time. When the lamp first started swinging, and it had a large arc, it moved quickly through the arc. Later on, when the swinging had died down, and the arc was smaller, it swung more slowly through the smaller arcs, but the total amount of time for each complete swing was always exactly the same. How did he determine that? Well, he timed the swings by counting his own pulse. I've often wondered about that, having realized that he was making a great discovery why his pulse didn't start racing and ruin his own measurement. But in any case, he timed his own pulse. Now, I figured each complete swing of that lamp must have taken about 5 or 6 seconds, and you had to watch it go through many, many complete swings as the motion got smaller and smaller, counting his pulse each time to make sure that each swing took the same amount of time. It must have been a very dull sermon. The lamp is still there in the Duomo in Pisa. It's called Galileo's lamp, and for a few hundred lira, you can buy a picture of it from the enterprising street vendors outside on the piazza. And so you see, it really is a good story. The only thing wrong with it is that according to the church records, the lamp wasn't installed until 10 years after Galileo died. But Galileo really did make that discovery, and it was extremely important, because what he had discovered was that a pendulum could be used as a timing element. And in fact, his discovery led immediately and directly to the invention of the first accurate clocks. The kind of motion he was studying is called simple harmonic motion.
Cool.
Bobbing up and down on an ordinary spring, this simple weight repeats itself once every second.
This looks familiar to me.
As time passes, its motion dies down, its excursions become smaller. But it still takes exactly 1 second to make each cycle. It is a perfect timekeeping device. And its motion is called simple harmonic motion.
Dun-dun-dun. It sounds like there's crickets in the background. You can hear the spring, you know?
Well, they're trying to emphasize the 1 second per cycle, and the cycle goes up and down. 1, 2, 3, up and down.
Okay, so that was our first little segment there. If a spring is strained from equilibrium and released, it will oscillate back and forth.
And we saw that too, didn't we?
Yeah, we saw that over here.
With these things. That's what we're talking about.
Okay, so back to the video.
538 to 654. 538. That's good.
In the language of classical mechanics, force. The F in Isaac Newton's F equals mass times acceleration.
There are forces going on here, and accelerations.
In a certain position, all forces are balanced. However, when the spring is stretched, it attempts to pull the mass back to its original position. The farther the mass moves, the greater the force to pull it back. The same principle works conversely. When the spring is compressed, it tries to push the mass back. Whichever direction the mass moves, a force emerges to counter the displacement. The combination of this force and the mass's inertia will be the key to keeping time. At each point in its motion, the net force is proportional to the distance x of the mass from its equilibrium position and in the opposite direction. The equation is F equals minus kx.
Hooke's law.
The value of k depends on how stiff the spring is.
Okay,
Oh, is that it?
I think so. Yeah.
I was getting like, I was really zoned in there. I was like,
It's good stuff. It
I was
is.
like, oh, this is making sense. Oh,
Well,
yeah.
that's why we're showing it.
Oh, yeah. Nice visuals there. Okay. So let that sink in. If you had any questions, you need to see it again, go ahead and replay it. I like how it had like it had the X and the force, and it had them flip flopping. Like
Yeah,
that.
it's
That was nice.
great animation.
Okay, so here we are. This simple harmonic motion, abbreviation SHM, has a period and a frequency to its oscillation.
Here are a couple of very important ideas. What period is this right now?
We're in zero period. And how long is zero period? Okay, so period, T, is the time for one cycle.
Yep.
And the frequency, F, is the number of cycles in 1 second.
Time
So-
for one cycle and the number of cycles in 1 second.
So they're opposite of each other.
They're inverse
They're
of each other.
inverses. That's the word I was looking for.
Yeah.
And you can see that in their units, which is kind of cool.
Yeah.
Seconds per cycle and cycles per second, or a hertz.
Yeah, it's a derived unit that you see in frequency.
Yeah.
Period is how much time it takes for one cycle, and frequency is how many cycles per second. It's like clapping your hands fast and slow. Show them that, would you, Ms. Moore?
Okay.
You got
So-
slow, long time between each clap, and there's short time between each clap. But when you clap fast, that's a bunch of them every second, right?
Yes, yes.
And if you clap slow, that's fewer per second.
So higher frequency versus lower frequency. Okay. So amplitude, A, is the maximum displacement from equilibrium. The spring moves.
Okay.
Frequency is unaffected by amplitude.
That's what they just said. We have a very small amplitude here, but the frequency doesn't change if we have a larger amplitude.
Nice demonstration. Okay.
That's right.
And you guys have probably heard these terms before, which is nice. Okay, back to our video. Okay, 1709 for this one. Back at it again.
So I find 13.
1309. Is that what I said?
It's from 13 to 1709.
Yeah, you're right. 13 to 17. That's when we checked out earlier.
That's good. There you go.
Right on the money.
Nailed it.
With natural precision. They lack precise intervals, repeating forever according to an inexorable law of nature. Human imitations of the great clock of the heavens are based on a different but equally inexorable law.
The most inexorable law in mechanics is F equals m times a, the second derivative of x.
That thing on the
In
right
simple
is
harmonic motion, force comes from the displacement x itself. F equals minus kx. Together, these two equations give the differential equation that describes
This is acceleration.
that's just acceleration right there. Is expressed in a differential form or
Woohoo,
calculus.
calculus.
That's right.
simple harmonic motion.
You'll get there in college.
Yeah.
That differential equation refers not only to a mass on a spring, but to any physical system that, when disturbed, is restored toward equilibrium with a force proportional to the disturbance.
Hooke's law.
For example, the pressure of the air in an organ pipe, or the angle of a pendulum, the bending of a tuning fork, or the rotation of a clock movement. These systems and many others undergo harmonic oscillations. These oscillations can be too fast to see, at least under normal circumstances, or too slow to wait for.
That's the moon.
Or they can be any other frequency, high or low. No matter the frequency, however, they can all be described by the same differential equation. The differential equation is solved by the time-honored technique of guessing.
It's true.
A long time ago, someone guessed that the solution may be a sine function. It was an educated guess, because the motion of a mass oscillating on a spring resembles the motion of the shadow of a particle moving in uniform circular motion.
This is important. What's making those shadows? Something going around a circle?
So the idea of guessing a sine function seemed quite natural. In this case, a sine function with amplitude A and angular frequency omega.
Pause right there. New term. Angular frequency for omega.
Yeah, we'll give them that.
But if that's x,
Look at this guy.
is
I
its
know.
second derivative equal to minus k over m times x?
I wish I had one of these machines.
Oh wait.
First derivative. Second derivative. We'll take a look at this equation in a minute.
The answer is yes, if omega is chosen correctly.
Whoa!
Woo, that's important.
For the mass on a spring, the angular frequency is equal to the square root of k over m. The stiffer the spring, the higher the frequency. The greater the mass, the lower the frequency. But whatever the frequency, it depends on the mechanical properties of the oscillator, such as the mass and the spring constant.
That's right.
The time needed to make a complete cycle does not depend on how big the swings are, represented by A in the equation for x.
Amplitude.
So even as the oscillations die down, harmonic oscillators continue to keep perfect time. The frequency is measured in radians
Oh,
per
wait.
second.
No, wait a minute.
There are 2 pi radians in each
yeah.
complete cycle.
No, I think that's it.
Pause there. Okay. All right. And you know, with the little machine that was cranking out these equations, that's calculus. And we are an algebra-based physics class, in case you hadn't noticed. So don't worry about that. You can learn about that
Your calculus class.
in your calculus class. Yeah.
Calculus was invented by Sir Isaac Newton
Go
in
figure.
order to explain the functioning of the universe.
All right. So here we go. Oh I'm over there on the wrong side. Here we go. I just opened up a periodic table over there. Okay. So let's talk about this equation.
It's a review right there.
A ball going around the unit circle moves with an angular speed of omega, where our omega, our angular velocity, is 2 pi over t, and radians per second.
Yeah,
Right?
and t is the period, that's the time to go around once.
Wherein 2 pi is 2 pi radians is the whole
Circumference.
circumference of a circle.
Yeah.
Okay.
Well-
The shadow of this ball. So remember in the video, right? The thing was going around the circle, and as you looked on the wall, the shadow of this ball exhibits simple harmonic motion, where omega is called angular frequency as opposed to angular velocity.
Yep.
Because it's going up and down and not in a circle. That's the shadow. We can take this our period, our t. T is equal to is the inverse of f, and so we can basically put f right there.
Yep. T is seconds per cycle. Frequency is cycles per second.
Yeah. So like this, right?
Or you could have F is
Okay,
equal to 1 over T.
Or f equals 1 over t. And so where we have that 1 over t, we just went ahead and put that F
Boom,
right
boom,
there.
boom, boom, boom.
Okay. So this equation is important.
Yep.
Starting from x max, the position of the shadow on the x-axis depends on the amplitude, the angular velocity, and the time.
Yeah, and what this is basically with the equation we saw is where is it at any particular moment as it goes up and down depends on the total amplitude, how far it's going, its speed, its angular frequency, and what time you want to know about.
Yeah, what time are we talking about?
Yeah.
So, and this equation, we're not going to be doing any practice problems with it, but the idea is you can know where the location of it is.
And basically what you've got is words, 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 words. Equation says the same thing.
Okay, so how are these alike? This is the equation we just showed you.
Yep.
And then down here, we have this 2 pi frequency times t. And how are these two alike? Well, we said that this is this on the 2 slides before, so
yeah,
we just put it
it's
in
the
there.
same thing.
Right?
So if you can choose whichever one you need depending on the situation.
Okay, so our next question, what happens to the velocity of the mass on a spring as it oscillates? Okay, so here is our mass on a spring. And what's happening to the velocity? Where is it going the fastest? Where is it going the slowest?
That's going too fast. Put another mass on there, would you?
Okay, let's slow her down. Okay, ooh, here we go.
What happens to the speed as it goes up and down?
Huh, this reminds me of the pendulum,
Yeah.
right? So am I answering this question right now?
Well,
I can't remember if it's on the next slide or not.
here it is at equilibrium, kinda. If I give it a little shove away from equilibrium, where's it going the fastest? Where's it going the slowest?
It looks like it's going the fastest in the middle right there.
Yeah.
And it comes to a stop at the top and the bottom and changes direction. So it's going the slowest at the top and the bottom.
That's right.
Yeah. We'll just leave it there to do its thing. Okay. So starting with t equals 0 at equilibrium, the velocity at time t is this. So what does this tell us? Well, this tells us that that velocity is changing,
Yeah.
right? There are variables, the amplitude, the angular frequency, and the time, and based on what those numbers are, our velocity is going to
The
be
velocity at any particular time depends on this stuff right here.
changing. Okay, I think that's good for that.
That's good. Yeah.
Then this one. Vmax happens as the mass passes the equilibrium point.
The equilibrium point is masculine.
No, we won't gender our
Gender
equilibrium.
identify here.
Okay, so so this is exactly what we just talked about. The maximum velocity is going to be at that equilibrium point in the middle. And you know, in case you're like, Miss Moore, I still don't see where the equilibrium point is. Well,
Just stop it.
the equilibrium point is right there.
The up is canceled out by the down.
Yes.
It's at equilibrium. If you pull it down below that, up is bigger than the down. The force up is bigger than the force down. If you pull it above equilibrium, the force down is greater than the force up.
Why do I know that? Because it
And
goes down.
yeah,
So what was it again? Yeah. So when we have it oscillating, the Vmax is going to be right in that middle area because it's using all of its force. The force is the restoring force trying to get it back to the middle, so it's going to be using all of its effort to get it back.
yeah.
There. Okay. Oh, I just.
We just explained
Why is
this.
that the fastest point? Okay, so why is that the fastest point? I think we're good on that one.
Yeah.
What happens to the restoring force as the mass oscillates? I kind of just talked about
That was one of the really good illustrations on the video where it
Oh,
had
yeah.
the displacement and the force.
Yeah. So if the displacement was this way and it had the force that way, and that's the restoring force,
Yep.
right? I don't know if the displacement was this way, the restoring force was that way. So, you know, what happens to the restoring force as the mass oscillates?
Continually changes.
Where would the restoring force be greatest, least?
Well, it'd be least at equilibrium. It'd go to 0 at equilibrium because the
Yeah.
forces are equal.
Yeah, and the middle, it's the restoring force is the least because, well, the restoring force is 0 at this point.
Yeah, because the up cancels out the down.
But they're the greatest, you know, at this point and that point, this point and that point.
The farthest extent from equilibrium.
The top and the bottom, you know? Okay. The top, bottom of the oscillation. All right, so what about the acceleration of the mass as it oscillates?
Well, let me answer this one, okay? F equals ma. And so the acceleration is proportional to the force. So if the force is 0, what's the acceleration?
0.
Yeah. And if the force is max, what's the acceleration?
Max.
So, boys and girls, what's the relationship between the acceleration and the position in the oscillation?
Well, we also have an equation for this too.
Yeah.
And again, we're not going to be doing any problems with this, but you know, the idea is that the acceleration is changing, and the acceleration is going to be be 0 in the middle.
Yep.
And it's going to be, and then it changes as it goes to the top and the
Yep.
bottom. Okay.
And all of this is based on t being 0 at equilibrium.
Yes.
So if t is at 0, you set the stopwatch starts when it passes equilibrium, and as it goes up and down, if t is 0, acceleration is 0. Boom, boom, boom.
Okay. So what determines how fast the spring went up and down? Oh, this was a good
Let's
question.
play with it. Let's play with this stuff.
Yes, okay. So let me go ahead and take this off here.
We've got the 2 springs, the gray one.
Okay, so should I just do them at the same time?
Yeah.
Here? Okay, so here we go. Which one's going faster? It's,
That-
I didn't do this one very well. It's
Yeah,
hard
the
with my
trick is if you put it,
hard with my left hand. Which one's going faster? This one
one
is,
on the
right?
right's going faster.
Okay.
It's a stiffer spring.
So same masses, but this one is a stiffer spring. Stiffer spring goes faster.
Put another one on the stiffer spring.
Okay, so boing, boing, boing.
Put
boing,
another one on the
boing,
stiffer
boing.
spring.
Okay. And here, get on there. Oop. Boing,
Slower.
boing, boing, boing. Okay, well that makes sense, right? Because I think the video talked about how if it has more mass, it's gonna have more inertia, and it's gonna go slower,
Yep.
depending on what's the shape, the moment of inertia.
Yep.
So we know that it varies with 2 things: the spring constant K, because the spring itself,
Yeah.
and then the amount of mass that's on there. And voila! For a spring oscillating with simple harmonic motion, the frequency varies with the spring constant and the mass.
That's an important equation right there.
Yeah, and when we say frequency, this is our angular frequency, the square root of the spring constant over.
It's really a simple thing, and they showed us that in the video where you got a fatter spring, it increased the spring constant, and the angular frequency was greater. When they had more mass on the bottom, as the number on the bottom gets larger, the whole fraction gets smaller, it slowed down, and we saw that just a moment ago.
Yes. Okay, so now, Ms. Moore, what about practice? We need to practice. Oh, I'm glad you asked. Oh, not yet, sorry, one more slide. So we also can say that, omega,
So that's what we just saw.
yeah.
But what is omega?
Omega is also radians radians per second, 2 pi over t, the period, which we know is also 2 pi times the frequency.
Cycles per second and seconds per cycle. So how could you solve that for K? Well, it would depend on if you had the frequency or the period. Frequency. Now you have this written down, right, boys and girls? If you haven't got it written down, write it down now because you're going to need it.
Yeah, so in order to get rid of this, you just square this, right?
That's right.
Right, so you'd square here and say you wanted,
You square everything else.
Square this. This would go away. This is everything squared. If you wanted to solve for the constant, you just multiply. You guys get the point.
Yeah.
Okay, so you can do it. Easy stuff. Okay. Now, this is your homework. Use the data for the period of oscillation from the spring lab to find the spring constant. Period of oscillation.
You've got them.
And you guys can just, write it up top here or something, or on the side.
So this period of oscillation is the letter capital T, right? So you got capital T, you got T, solve for K.
Okay,
So ignore this over here. Ignore that over there. You're just working with those things in the middle. On your mark, get set. You
Oh
can-
wait, actually also, don't forget, I want you to also answer, I've got the answers over here. Okay, I want you to also do the 2 lab questions at the bottom. Boom
You can
and
do
boom.
this.
Okay.
All right.
All right, now go for it.